Now we're going to get into a type of relationship that involves exponential, relations between two variables. Up till now, we've looked at linear and quadratic relations. And so we know linear, obviously, picturing the graph is probably easiest. If you picture the graph of a linear relation, it's a straight line, you use a ruler to draw it. Quadratic relations always look like parabolas, upside down U's or right side up U's, but always a U. But not everything is linear or quadratic. In the real world, a lot of things follow what's called exponential relations. So, some examples of that are growth of bacteria, compound interest, in other words, money earned on investments, rate of decay of radioactive materials. They are all modeled by exponential relationships. So, let's just dive into them. Here's a couple tables. If we look at A part, we have a table that this is a table of an exponential relationship. So as you can see, we still have all the x values, we still have all the y values. Obviously nothing changes as far as that goes. But we're going to see that if we want to make an equation out of them or a graph out of them, they're not going to look like linear or quadratic ones. So let's start with the graph and see how that's going to look. So all of these are ordered pairs, of course, right? So I can take the ordered pair, -1, and then the y value of a half, and put a point there. So at -1 on the x-axis, y value of a half on the y-axis. Let's do this one here in green. Actually, let's make this a little bit bigger so it's easier to plot. All right, what's the next point? We had 0, 1. Oh, sorry, I got to backtrack for a second though, because I just noticed, and this is an important thing to pay attention to, I just noticed my scale is going up by 2's. Notice how this goes 2 and then 4 and then 6 and then 8. I've got to pay attention to that when I'm graphing. So let me start over again. So -1, and then a half is going to be more like down here. And then 0, 1 is going to actually be here, halfway between the 0 and the 2. And then we have 1, 2, and then we have 2 on the x-axis and 4 on the y-axis. And then we've got 3 and 8, which is here. And then we've got 4, 16, and 5, 32. If I connect these dots, we'll recognize it, or we won't recognize this. This is not linear. This is not quadratic. It's not a U shape. It's not a straight line. It's sort of more of a slope, right? Sort of looks like a child's drawing of a ski hill or something like that. So it's got this slope sort of look to it. On the left side, it's flat. It's getting closer and closer to being flat. It's never going to go below the x-axis, at least not the way it's trending right now. And on the right side of the graph, it's getting steeper and steeper. All right, let's take a look at this one here on the right. Sorry, again, I just want to make my pen a bit bigger. So we got this ordered pair here that is 0, 27, then we got 2, 9, and so on. So we can plot those. -3, 27 is up here. Again, pay attention to the scale. This time it's going up by 3 as it goes 3, 6, 9, 12 on the y-axis. X-axis is going up by 1s. I got the point 2, 9, which is down here. I got the point 1, -1, 3, and -2, 9. I got 0, 1, which is going to be way down here. Now I'm getting these really small fractional numbers. It's going to be hard for me to draw them accurately, but I'll try. So I've got 1 and 1/9. I've got 2 and 1/27. Well, I can't be very accurate. But what I can do is that you notice how I'm not getting into negative numbers on my y's. They're always staying positive. So that's a feature we should pay attention to. So it's not dipping below the y-axis. Shouldn't come up again either, but it should be getting closer and closer to the x-axis. It's not dipping below the x-axis. I think I said y a second ago. So it's staying above the x-axis, but it's getting flatter and flatter. Again, it's got that slope look to it. It's not a U, it's not straight. This is an exponential function. we read graphs from left to right. So if I read this green graph from left to right, it's going upwards, isn't it? Well, that's why we're going to call this growth, exponential growth. It goes up. All right, then we've got our other one, and again, if we read the red one from left to right, it's going downwards. It starts up high and gets flatter and flatter as it goes along. When something does that, we call that decay, exponential decay. It's going down, goes down. So those are the two types of exponential relations that we can see, growth or decay. And we talk about that a bit below here. The graph of an exponential relation is a curve that is approximately horizontal at one end, increases or decreases rapidly at the other end. The two graphs you just sketched are exponential graphs. The one on the left is called exponential growth because it is increasing as the x values get bigger. The one on the right is called exponential decay because it is decreasing as the x values get bigger. All right. Another way to recognize exponential relations is to calculate the ratio of successive y values. If they are constant, you have an exponential relationship. So now we want to talk about ratios. And this is like what you've done before, where you've calculated first differences. Remember where you subtracted things to see if you had the same first differences all the time? That made it linear. If that didn't work, you tried subtracting the first differences, and if the second differences were all the same, that made it quadratic. Well, for exponential ones, we're not subtracting, we're dividing or multiplying. We're going to divide in this case and see if we get a common ratio. Ratio just means that it's related by multiplication and division. So if I were to take 1, this one here, and divide it by a half, well, how many times does a half go into 1? It goes into 1 2 times, right? So I'm not subtracting. Again, for first differences, I'd subtract the first one from the second one. In this case, I'm dividing the second one by the first one. What about if I took this number 2 and divided it by 1? So again, I can go down with my y values and see what's happening, but again, it's by division, it's not by adding or subtracting. And then carrying on, 4 divided by 2. Well, guess what? That also equals 2. 8 divided by 4. That equals 2. 16 divided by 8. That equals 2. I see I wrote down the wrong thing here. I should have written a 4 here. And the last one was 32 divided by 16. So every one of these is the same. But we didn't get it by subtracting, we got it by dividing. So each one is twice as big as the previous one, right? So the common ratio is 2. So no common difference, but common ratio for exponential functions. So it's the ratio of successive y values in each of the tables above are constant. We know that two relations expressed in the tables of values are exponential. So in other words, without even looking at the graph, if I was to graph this particular one, this bunch of ordered pairs, then the graph would look like an exponential graph, as we've seen already. If I was to, so in fact, let's go back to the tables that we previously looked at. This table is really the exact same table as this green one, I think, yeah. But if I look at the red one, let's see what's going on for this one as far as the difference. We already know it's exponential, which means there should be a common ratio. 9 divided by 27 equals 1/3. 3 divided by 9 equals 1/3. 1 divided by 3 equals 1/3, etc. So it's got a common ratio again. And it's no accident that this common ratio is a fraction between 0 and 1. That's what makes it decay. The fact that this one, the green one, that we've done on the next page down has got a common ratio of 2, a number bigger than 1, that's what makes this growth. Okay, so there's a connection between these things. Again, there's lots of real-life relationships that use ratios. One of them is value of things, such as this example here. A car purchased for $60,000 depreciates by 20% each year. This can be represented by this equation right here. V equals 60,000 times 0.80 to the exponent t, where V is the value of the car and T is the time in years since it's been purchased. This is actually our first look at an example of an exponential equation. We're going to come back to these a lot in the next couple lessons, but this is an exponential relationship. What makes it special, what makes it exponential, is that the variable, one of the two variables anyway, is the exponent. Think about what we already know. Think about quadratic. In quadratic relationships, the most basic ones are, let me do it in a different color. The most basic one is something like x squared. That's quadratic. However, if I have y equals, for example, 2 to the x, exact same variables, just in a different place, that makes something exponential. So we're going to recognize exponential equations by the fact that the exponent is the variable. So this one that I've highlighted in yellow, it's got different variables. It's got v and t, but t is like my x variable, and it is my variable is the exponent, making this whole thing exponential. So anyway, this is an exponential relation, but we don't even need to worry about that too much to answer this question. We just need to put numbers in the right place. This value is t, so t equals 1. So I can just go v equals 60,000, 0.80, or just 0.8 to the 1. So I'll replace t with 1. And then I have to follow order of operations. I can just type it in my calculator, but if I were to follow order of operations myself, 0.8 times 1 is 0.8, multiply that times 60,000, and I get $48,000. So what this tells me is the car is decreased to $48,000 from $60,000 that originally was. 3 years, again, this is my t value here, t equals 3, so v equals 60,000 times 0.8 to the 3. Again, following order of operations, 0.8 to the 3 comes first, and it's a smaller number, and then I multiply that by 60,000, and it works out to be 30,720. So, as time goes on, the value of the car is going down. That makes perfect sense, of course. It should go down over time. So this one is decay. And again, I'm getting ahead of myself a little bit, but remember we talked about a common ratio. So for growth, the common ratio in the example above was, example 2 was 2. In example 1, we saw that for decay, the common ratio was 1/3. If we look at this equation that we're using here, the common ratio shows up as the base of our power, and so that 0.8 is actually our common ratio. If I had a table of values and I was trying to work out what the common ratio was based on this equation, this would be my common ratio. And The fact that it's 0.8, a number between 0 and 1, is what shows me its decay. It's showing me that the value of the car is going down over time.